Ever wondered how a robotic arm can twist, turn, and reach with such incredible precision, mimicking human-like dexterity? The secret lies directly in their joints, which are the fundamental elements dictating a robot's degrees of freedom, often abbreviated as DOF. A robot's degrees of freedom quantify the number of independent parameters required to define its configuration or pose in space. Each joint in a robotic mechanism contributes specific degrees of freedom by permitting a certain type of relative motion between its connected links. The two primary types of joints are revolute joints, which allow rotational movement around a single axis, and prismatic joints, which enable linear sliding motion along a single axis. Crucially, each of these simple joints typically provides one degree of freedom. However, more complex joints, like spherical or universal joints, can contribute multiple degrees of freedom. For instance, a spherical joint akin to a shoulder can offer 3 rotational degrees of freedom, while a universal joint permits 2. Engineers systematically sum these individual joint contributions to determine the total degrees of freedom for an entire robotic manipulator. This calculation allows designers to ensure a robot has sufficient DOF to execute its intended tasks, whether that is intricate assembly, complex grasping, or precise trajectory following. This fundamental understanding is pivotal for kinematic analysis and control system design. The concept of degrees of freedom is not just about counting movements. It also ties into the robot's workspace and dexterity. A robot with 6 degrees of freedom, typically achieved with a combination of revolute and prismatic joints, can position and orient an end effector anywhere within its workspace. This 6DOF configuration is often referred to as full pose control. More advanced manipulators may possess redundant degrees of freedom, meaning they have more than 6DOF. This redundancy enables them to perform tasks while simultaneously avoiding obstacles, optimizing joint limits, or navigating singularities. Understanding how joints contribute to a robot's degrees of freedom is therefore essential for designing effective, versatile, and controllable robotic systems, directly impacting their ability to interact with the world around them. It helps us predict and control their movements with precision and agility, unlocking their full potential for automation and complex tasks.
If you love robotics, like, subscribe, and keep building with us.